Okay, so rank the following acids by strongest acid to the weakest. What are we supposed to do right from the start? Conjugate bases. So I'm just going to do that shorthand, okay? I'll just scratch that out and put a negative charge. Scratch that out, negative charge. So here's our conjugate bases. And that would get rid of this. So we have one hydrogen on that oxygen atom. Now, if we go through the cardinal rule, or you could use the Orgo rule, but I don't know how to use that. Okay. What are we supposed to do? When we look at those 5 conjugate bases, we see charge. Okay. We are looking at the stability of the conjugate bases. Okay. So if we have a y-axis, okay, which one's going to be at the bottom of that energy diagram? Okay, so let's not worry about which molecule. Let's just say the bottom one is going to be the most stable, because as we go up on the y-axis, that's increasing in instability. Right? Lower you are in energy, the more stable. So we are asking the question using the cardinal rule. Which of those conjugate bases is the most stable? And the cardinal rule says C for charge. So this one, E has no charge, and A through D have charges. So that makes this conjugate base the most stable conjugate base. So that's the most stable conjugate base, which makes it the acid form the stronger acid. Okay, so the most acidic would be E, because its conjugate base is the most stable. Because remember, why does the proton want to give up the proton if it's going to go to instability? It's willing to give up the proton if it doesn't hurt so much. But if it's going to hurt a lot, that's going to hold on to that proton, saying, you're not touching that thing. Because if you take that proton from me, life is going to be miserable. So it holds on to it tightly. And how do we assess that tightness? pKa's or Ka's. Okay, so we use the cardinal rule to find charge. But now when we look at A, B, C, and D, they all have a charge. So we don't use that letter. Now we go to A, which is for atom. A has a negative charge on oxygen. B has a charge on carbon. C has a charge on oxygen. D has a charge on carbon. So which atom can stabilize the negative charge better? Oxygen. So what principle are we using? Electronegativity. And why are we using electronegativity instead of a size argument? Because oxygen and carbon are in the same period. So that's an electronegativity argument. If we're going down a column or a group, then that's a size argument. So because we're dealing with oxygen is the most stable, we have E that's the most stable. Now, between A and C, which one's the next most stable? Okay, I'm ignoring molecules B and D. Why? Because the negative charge is on carbon. I'm focusing just on oxygen, because that's going to be the next most stable thing. So when I take a look at A, I have a negative charge on oxygen, and I have on C a negative charge on oxygen. Can I break the tie with that analysis? No. So the cardinal rule says, okay, go to resonance and delocalization. Does A have resonance structures? Yes, you can draw those. And then C also has resonance structures. So we've ran into another tie. Now we're going to use induction. And clearly, molecule C has those fluorines that are going to stabilize that negative charge by induction. So that means C is the next most stable conjugate base. So that would make that C as the stronger acid. And then, it's just by default, A would have to be the next one. Now, we cross those out. Those are done. Now it's just between B and D. We see that the negative charge is on the same atom, right? I'm messing that up. Okay, so what does B have or D have that, how are we going to break the tie? Charge is the same, atom is the same, resonance. Do they both have resonance? Yes, they do. But here's the trick here. The more resonant structures that you can draw, the more stable the molecule is going to be. So if we take a look at B and compare it to D. Okay, it looks something like this. We have a negative charge there. Negative charge means there's a lone pair, right? So that could resonate in that direction. That's one resonant structure. Or we could say, hey, let's take that lone pair and resonate this way. Whereas molecule D, oh, there's no oxygen there. Molecule D only has one resonance structure. So between those two options there, we would say molecule B is more stable than D because it has more resonance structures. So that's more stable, so that's B, and then D would be the last. Do you see the reasoning behind all this stuff? So just memorizing facts is going to do it. There's that component. You have to memorize and learn things. But being able to apply these principles and rules is the goal. Okay? Are there any questions about that process? Yeah. Why did that hydrogen break? Because this hydrogen broke right here, or is the acidic one, because it's sandwiched between two carbonyls. It's going to be stabilized by the resonance. All the other carbons isn't going to be as stabilized. So if we continue on, looking at the conjugate bases of the above acids. Okay? Draw the conjugate base that is the strongest base. So what have we done? We've layered our stabilities, right, of the conjugate bases. Molecule E is at the bottom, and the conjugate base of D is at the top. So D is the least stable conjugate base. So if it's the least stable, what is it thinking it wants to do? If it reacts, then it becomes stable. And so the most reactive, or the least stable conjugate base is like, this sucks, and the only way out of this mess is if I find a proton. And so it's like, and grabs a proton as fast as it can. So the conjugate base of D, because it's the most unstable, it's going to be the most reactive. And if it's the most reactive, that makes it the stronger base. So the conjugate base of D looks like this. All right? That's the strongest base. Okay, now does that make sense? We clear with that? Okay, so why are we chatting? We still have a couple of minutes, and I want to answer that last question here. Yeah. You have to draw the resonance. It depends on what the question's asking. That is the conjugate base. There's no need to draw a resonance structure. Okay, can I finish the last question? Okay, looking at the molecules at the top of the page, what it's trying to say is just look at the acids. Okay, look at those guys right there. Okay? I know they're acids, class, but let's just call them bases. Which one would be the strongest base? It would have to be D. Okay? Why would D be the strongest base? Because it is the weakest acid. Remember that correlation? The weakest acid means it's going to be the stronger base. Okay? Okay, well, those people who have questions, just come on up and you guys have a good rest of your day.